Hello, this is Mr. Stansbury. I'm going to take you through the notes on the area under a curve. At the end of this, you should be able to say, I can use integration to find the area under a curve. All right, so with integration, we can look at the Riemann integral in a new way. Okay, so f of x is positive and continuous on the interval. So here's our f of x, positive and continuous. A, where x is between a and b, so here's our between a and b, then bounded by y equals f of x, whatever our function is, the x-axis, and then the vertical lines x equals a and x equals b is given by this here, the definite integral of f of x from a to b, right, with respect to x, right, or you can rewrite it like this as well. Okay, so using this idea, find the area of the region enclosed by y equals x plus 1, the x-axis, and x equals 0 and x equals 3, using a geometric argument and then integration. Okay, so I took a few seconds here to draw this out. So here's the y equals x plus 1 line right here. And then right here, here's our line that's where we've got x equals 0, 1, 2, 3. Here's where x equals 3, right? And then we also have the x-axis here. So basically they're saying we want to try to find this area right in here, right? So we're looking for that. So if we're using a geometric argument, with this, there's really a couple ways we can do it. We can actually, we can go through and we can just do this, right? We can just kind of draw our little lines in here, kind of follow my drift here, and then literally you can count the boxes. 1, 2, 3, 4, 5, 6. This and this together makes 7, and then there's another half right there, so that would be 7.5. A little bit more formulaic way to do it is to do a trapezoid, right? So the area of a trapezoid is, we take the base 1 plus base 2 divided by 2 and multiplied by the height. So if we look at base 1, we can call that this over here. So that's 1. Base 2 over here is 1, 2, 3, 4. Take that divided by 2, multiply by the height, which would be this right here, which is 1, 2, 3. So that's 5 halves times 3, or 2.5 times 3, which guess what is also 7.5. Same thing there. Okay. We can also figure this out with integration, right? So we can calculate that using the definite integral from 0 to 3. And we put our function in here, which is x plus 1 with respect to x, right? So we can actually do that on the calculator. I'll show you that here in a second. But what we're going to do is we're going to do the antiderivative piece on this, right? So that is officially x to the 0 over here. This is x to the first. Actually, you know what? Let's do this over here on the side. So we've got x to the first plus 1 x to the 0. So if we're going to do the antiderivative, remember we add 1 to the exponents and then take whatever that new power is and divide by it, right? So we've got x squared over 2 plus x to the first over 1, right? Which is just x, 1 half x squared plus 1, plus x, sorry. Okay? And then we can rewrite that, right? And we can just leave it like this. We do not need the constant of integration on our definite integral here. So we would then write, remember this, we do say, let's do 1 half x squared plus x. And then we are going to do that from 3 to 0. So this is, if you'll remember, this is where we plug in 3 to this, figure out what we get, and subtract what we get when we plug 0 in for this. So 3 squared is 9. Half of 9 is 4.5. And then plug in 3 for x. Oops. So that is going to be, for just the 3 part, that's 4.5 plus 3. Right? We take that whole thing, and then we're going to subtract. When we plug 0 in there, that's 0 plus 0. So guess what? 4.5 plus 3 is 7.5 minus 0 gives us 7.5 square units that way as well. Okay, and then just one last way to do this. So literally we're going through 4 different ways how to do this here. We can go into math, and then we're going to go into function at this number 9 here. Right, and we're going to go from 0 to 3. And we're going to put in our original function, right? So we'll do x plus 1 with respect to x. And simply push enter. And there's our 7.5 that way as well. So calculator also gives us 7.5 when we do our integral on that, our definite integral. And then we, let's show a 5th way just because we can. So we can put x plus 1, our function, our original function, in there. And, okay, and then here's the graph of that. Then all we'll do is do second trace, and we'll choose number 7 here. And then we're going to want to do lower limit is 0. And our upper limit is 3. And it's going to go through and shade that in and tell us again, one more time, that it is 7.5 from the graph. 1, 2, 3, 4, 5 different ways to figure that out. Okay? Okay, let's take a look at one last example here. Example 11. Find the area of the region enclosed by y equals 1/2 x squared plus 2. The x-axis, x equals 0, and x equals 3. So we're not going to try to do this geometrically. That'd be a little trickier, but we can do it with the graphing calculator. And then we also want to try it with our good old definite integrals and our antiderivative, right? So we got from 0 to 3, and then we have 1/2 x squared plus 2. So if we do the antiderivative on that, 1/2 x squared plus 2x to the 0, add 1 to both of those and divide by what we have left. So that's going to be 1/2 x cubed, the whole thing over 3, right? Plus 2x divided by 1. So that's just going to be plus 2x, right? And then this one here, 1/2 our x cubed divided by 3. We can take that as 3 over 1 and flip it and multiply it. So it's 1 over 3, right? So really that's going to be 1/6 x cubed plus 2x. So we've got 1/6 x cubed plus 2x. And then remember, we can simply write it like this, from 0 to 3. This is where we plug 3 in and see what we get, and then plug in 0 and see what we get, and then add those together, and that will give us our area under the curve, right? So 3 cubed is what, 27? So we got 1/6 of 27 plus 2 times 3, right? So let's see, 1/6 of 27 gives us 4.5. So this is 4.5 plus 2 times 3 is 6. So this is going to be 10.5 units squared by doing it this way, basically by hand. And then let's double check this thing by also doing this with our graphing calculator. We can do it with the graph so you can see it, or we can use this number 9 here. Go from 0. Oh, not sorry. Let's see. 2. If you do go to on this, if you forget to put some other stuff in there, it'll just take you back to your original one. So 0, 3. Put in our function, which is 0.5 x squared plus 2. all with respect to x. And that also gives us 10.5 there as well, right? So check on that. And then again, one more time just for good measure. We can go into y equals, clear out what we have, and we can put in our 0.5 x squared plus 2. Give us a pretty little graph so you can see what's going on. So there's our graph. And then we do second trace and select number 7 there, our definite integral down there, and we're going to go from 0 to 3. And it's going to shade it in for us, show exactly what we're finding. And there again is 10.5 units squared. Okay? Okay. That's all we have for the area under a curve. If you have any further questions, please feel free to ask. Thanks.